Hi, hi everyone. Today we are going to see the next topic, that is mathematics of symmetric cryptography in the course Cryptography and Network Security. This course is developed by Jawaharlal Nehru Technological University, Kakinada, in association with Andhra Pradesh State Council of Higher Education. Myself, Dr. M. Sitaram, I'm working as Associate Professor in the Department of CSE, like Reddy Baladi College of Engineering. So before we start with the mathematics of symmetric cryptography, just we'll have a look at the Venn diagram of number system. So if you see this Venn diagram, the superset of all the number systems, we can consider it as complex numbers. So complex number, we doesn't have that much of works regarding the complex numbers in the cryptography. So again, in the complex numbers, we know that we'll have real numbers and we'll have imaginary numbers. We'll have real numbers and imaginary numbers. So this set is imaginary. Again, in the imaginary, we'll have pure imaginary numbers. Then coming to the real numbers is combination of rational and irrational numbers. Real numbers is a combination of rational and irrational numbers. So again, we doesn't have that much of importance to irrational numbers. We'll have rational numbers. Again, in the rational numbers, we can divide it into integers. Within the integers, we'll have whole numbers. Within the whole numbers, we'll have the natural numbers. So the difference between natural and whole numbers is in natural numbers, we don't have zero. Here we have zero. So integer sets we have already seen regarding the first unit. So whatever the values we consider from minus infinity to plus infinity, we can call them as integers, and the set of integers is going to be represented by z. You know that. So z, we know from this z we are taken in modulo operation and we call it as zn. We call it as zn. That's what we need to know. Basically, mainly we use z and zn here. Z and zn here. Okay. So this is regarding the number system. Now, group is a set of elements along with a binary operation which satisfies four properties. That is closure, associativity, it will have an identity element, it will have an inverse element. Along with these four properties, if it satisfies one more property, that is commutativity, then we call it as abelian group. So a ring is in the ring, we along with the binary operation, we have considered one more binary operation, that is second binary operation, is an algebraic structure with two operations. The first operation must satisfy all five properties required for an abelian group. What are the five properties? Just when we discussed. Closure property, associativity property, existence of an identity element, existence of an inverse element, and then finally commutative property. The second operation must satisfy only the first two and must be distributive over the first operation. So what are the first two? Closure and associativity. It should have closure and associativity. Along with these two, the second we should have a distributive property. So what does the distributive property says? If A star B dot C equal to A star B dot A dot C, and if you consider A dot B star C, it should be equal to A star C dot B star C. So whatever the value you are getting on the LHS, that should be equal to the RHS. Whatever the value you are getting in the LHS, that should be equal to the over the RHS. Now let us take this Z comma plus comma star. Okay. And check whether it is an ring or not. Let us check it is a ring or not. So what is the ring structure that we are considering? That is algebraic structure. Set of integers over the operations plus and multiplication, that is star. So we all know that Z comma plus is an abelian group. We all know that Z comma plus is an abelian. We already discussed when we discussed about groups. So then no problem. Now we need to check whether star satisfies the first two properties, that is closure property and associativity property. Okay, associative property. Now if I take any two elements, if I take 4 and I apply multiplication between 10 other value, the value that I am getting is 40. So it belongs to Z only. It belongs to Z only. So the second operation star satisfies the closure property. The second operation star satisfies the closure property. Now what about associativity property? So what does associativity property says? If 4 star 10 star 2 should be equal to 4 star 10 star 2. Okay. Now, what is 4 star? That is multiplication star. 4 into 10 is 40. Then I need to do multiplication with 2. Now, this should be equal to 4 star, that is multiplied with, what is 10 multiplied to? It is 20. Right? So 40 into 2 is 80. 4 into 20 is also 80. So the second operation also satisfies the first two properties, closure property and associative property. Now we need to check only one property, that is what? Distributive property over z comma plus comma star. So what is the distributive property? So let us consider same values. 4 plus 10 star 2 should be equal to 4 star 2 plus 10 star 2. Okay. Now what is 4 plus 10? 4 plus 10 is 14 into 2. Now what is 4 into 2? 8 plus, what is 2 into 10? 20. Okay. Now what is 4 star 2? It is 28. Now what is 8 plus 20? 28. So this satisfies the distributive property also. This satisfies the distributive property also. So we can say the group, or we can say the set Z, that is set of integers over the operations plus and star, is a ring, So I am again telling the properties a ring should satisfy. So if you consider a set of integers over two binary operations, now I can call it as a ring if the first thing, that is the set we are considering with the first operation, should be an abelian group, and the second operation should satisfy closure property, associativity property. Along with it, it should be distributive over the first operation over the given set. Then we can call it as a ring. Okay. Then we call it as a ring. So that's what the property of ring says. So ring denoted as R is equal to some set, whether it may be any set with two binary operations dot comma star, is an algebraic structure with two operations. Okay. Remember, in group we are considered only single operation. In ring we are considering two binary operations. Okay. The first operation must satisfy all 5 properties required by an abelian group. The second operation must satisfy only the first two, that is closure property and associativity property, and must be distributed over the first operation. So this is the distributed operation. Okay. So we can say that set of integers over the two binary operations, addition and multiplication, is a ring. So this is how we can represent it. So same, along if a ring satisfies a commutative property, then we call that ring as a commutative ring. Now the next thing is field. So a field denoted by F is equal to set of two binary operations dot comma star is a commutative ring in which the second operation satisfies all 5 properties defined for the first operation, except that the identity of the first operation has no inverse. Okay. This is what we call it as a field. So field should be a ring first. Which ring? It should be a commutative ring in which the second operation should satisfy all 5 properties. So already it satisfies 3 properties. Because it satisfies, so to become a ring, it should satisfy closure property and associativity property. closure property and associative property. Now, if I'm saying it is not a ring, it is a commutative ring. So if I'm saying it is commutative ring, it satisfies the third property also. Now, apart from these three, it should satisfy two properties, that is existence of identity element and existence of inverse element. And remember, the identity element of the first operation has no inverse in respect to the second operation. So this structure, this algebraic structure, we call it as a field. This algebraic structure, we call it as a field. Okay, we call it as a field. Okay. Now, what is a finite field? Although we have fields of infinite order, only finite fields extensively used in cryptography. A finite field, a field with a finite number of elements, are very important structures in cryptography. I told you, no. So what is a finite group and infinite group? So the set that we are considering here, if it is has an the set we are considering here have an infinite values, it is an infinite field. If the set we are considering here have an finite number of values, we call it as an finite field. So in cryptography, we have more importance to the finite fields only. Finite fields only, it doesn't have that much importance to the infinite fields. So what is Gallo showed that for a field to be finite, the number of elements should be p power n, where p is a prime and n is a positive integer. So he said that Gallo showed that for a field to be finite, the number of elements should be p. The number of elements should be p power n, where p is a prime and n is a positive integer. The finite fields are usually called Galo's fields and denoted by gf of p power n. So gf means what? Galo's field. Now gf of p is a field again, where we are taking this n as 1. When n is equal to 1, we have gf of p field. This field can be the set zp. Zp. So what is zp? All the values of residue modulo set over the value p. Residue modulo set over the value p. So 0, 1, 2 on to p minus 1. So with two arithmetic operation, addition and multiplication, recall that in this set, each element has an additive inverse and that non-zero element have an multiplicative inverse. So let us consider to see whether gf of 2 is an finite field or not. So gf2, first gf2 will have how many elements? 0 and 0 to n minus 1. So 2 minus 1, 0 comma 1. It has two elements, so it is a finite set. First, it is a finite set. Now we are considering two operation plus and dot. Over this, we are considering two operation plus and dot. Now, if you observe here, when I am applying plus, I am getting 0, 0, 1. Whatever the thing we are getting, those are all within the set only. So whenever applying z plus operation, I got 0 and 1, 1 and 0. When I apply the dot operation, I got 0 and 0, 1. So these elements belong to set only. So the properties is what? First closure property is satisfied. Next, what is the second property I need to satisfy for the both operations? That is associativity. Let us check whether the associative property is satisfied or not. So 0 plus 1 plus 1 should be equal to 0 plus 1 plus 1. Now, from this 0 plus 1 is what? 0 plus 1 is 1. What is, again, I need to apply 1 plus 1. So 1 plus 1 is 0. So it is from this one, I'll get it as 0. From this one, I'll get it as 0. So it says associative property is satisfied. Now, let us check associativity property with respect to the multiplication. Okay. So I'll take 0 dot 1 dot 1 should be equal to, what is the value I need to consider now? 0 dot 1 dot 1. Okay, so 0 dot 1 is 0, that is multiplied by 1 is 0. So I'll get, and again 0 dot 1 is 0. So finally I'm getting 0 here. Now what is the output of this one? 1.1. So what 1.1 is 1 and it is multiplied with 0, again I'm getting 0. So it is associative property also. So if I am doing addition operation with respect to 0, then I am getting whatever the value giving as input. So here the identity element is 0. Okay. Now if I do multiplication operation with 1 with respect to binary operation multiplication, whatever the value I'm giving. So with respect to multiplication, the identity element is 1. With respect to addition, the identity element is 0. So the third property is satisfied. Then what is the fourth property? So it should return, we have an inverse. It should have inverse. So if I am doing 0 with 0, I am getting 0. If I am doing addition with 1 plus 1, I am getting 0. So they are all self-inverse. So 0 is the inverse of 0, 1 is the inverse of 1 in the plus operation. Coming to the dot operation. So if I am doing 0 with 0 with 1 0, if I am going 1 with 0, I am getting it as 1. Okay. Now what are the inverse elements I need to see here? So these are the inverse elements. So a for 0 it is 1, for 1 it is 0. For 0, I don't have any inverse here. Why I don't have any inverse here? If you observe here, for 0, I don't have any inverse element. I'm not getting the identity element. So when I apply 0.0, I'm getting 0. When I'm applying 0.1, I'm getting 0. I don't have any inverse element. So when we have studied the definition of field, we said that the identity element of the first operation will not have inverse with respect to the second operation. So what is the identity element in the first operation? 0. So it should not have inverse here, right? So 0 don't have any inverse element. That's why 0 don't have any inverse element. So now I can call GF2 as a field, and it is a finite field. Here 2 is a prime number. This is so Galileo's field. It is a Galileo's field. So here addition or subtraction in GF of 2 is same as the XOR operation. Multiplication and division is same as the AND operation. Multiplication is also the same as AND operation. So this is like GF of 5. This is like GF of 5. So if you observe, they will satisfy all the properties. GF of 5 also satisfies all the properties. Like if you consider, we have the identity element for plus is 0. We consider the identity element for plus is 0. That is, when you apply here, we are getting all the values. We are getting all the values. So identity element for multiplication is 1. So when you are getting all the values. So every element we have an inverse, A2 inverse. Every inverse have an A2 inverse. Now, if I consider here 0, it should not have an multiplied in y, because 0 is the identity element in the first operation. So apart from that, everything is having the inverse with respect to multiplication. So this is also a finite field. Now we'll show the next, that is GF of 2 power n fields. GF of 2 power n fields. So 2 is a prime number. When we work with computers, the positive integers that are stored in the computer as n-bit word, in which n is either we can consider 8, 16, 32, 64, so on, right? So we can represent this 8, 16, 32 as an 2 power n. Okay, 2 power n. So the 2 power n value ranges from 0 to 2 power n minus 1, ranges from 0 to 2 power n minus 1. So we have two choices if we want to use it as a field. So we can use GF of P. We can use GF of P, that is Galileo's field with prime number P and taking power as 1. Okay, with the set ZP, where P is the largest prime number less than 2 power n, although this scheme works, it is inefficient because we cannot use the integers from P to 2 power n minus 1. For example, if I take n is equal to 4, so the largest, it is 2 power 4. 2 power 4. What is the 2 power 4 value? 2 power 4 is 16. So I can have values from 0 to so on. 2 power 4 minus 1, 15. I'll have up to 0 to 15. Now, here, what does Galileo's field says that the P value should be the prime number. So what is the largest prime number between 0 to 15 is 13. So I should take up to 13 only. If I take 13, the values will be up to 0 to 12 only. I'm writing again. Okay. For example, if I take n is equal to 4, what is the value possible? 2 power 4. Yeah, see, if I'm taking GF of 13 means I'm taking only the modulus operation, speaking about the modulus operation. So 2 power 4, 2 power 4. So 2 power 4 is equal to 16. So in the 16, from 1 to 16, what is the, so if it is 16, the values I will consider is from 0 to 2 power n minus 1. So it will be 0 to 15. So in between 0 and 15, what is the largest prime number? The largest prime number is 13. Largest prime number is what? 13. So if I'm taking GF of 13, I'm taking GF of 13, the values I'll consider is up to from 0 to 12 only, up to 0 to 12 only. Now I'm not using the values 13, 14 and 15, the values are wasted. Like that, if I consider 2 power 8, if I consider 2 power 8, the largest prime number is 251. So the remaining values I will not consider in my theory. So that is one of the drawback. If I consider it as, if I represent this GF of 2 power n as GF of P, that is Galileo's finite field. So we can work like that, this GF of 2 power 1 and uses a set of 2 power n elements. The element set are n bit words. For example, if you take n is equal to 3, I can represent them as like this. I can represent them like this. Okay. So this is how we go for the presentation of GF of 2 power n fields. GF of 2 power n fields. So let us define a GF of 2 power 2 field in which the set has 4 2-bit words. 4 2-bit words. So if I'm saying 2 power 2, I'll have 2-bit words. So it will be 0 0 0 1 1 0 and 1. We'll have 0 0 0 1 1 0 and 1 1. So we can redefine addition and multiplication for this field in such a way that all the properties of the operations are satisfied. That is, it should become a field. It should become a field. So we'll redefine that. So this is addition operation and this is the multiplication operation. So what I am considering is, I am considering a set of elements, that is 0 comma 0 0 1 1 0 1 1 over the operations plus and multiplication. Here I am going to take it as XOR and here I am going to take it as like this. Now this should be a finite field. Should be, because if it is a field, the number of elements in the set I'm considering is finite, so I can consider it as a finite field. Okay. So obviously it will provide closure property, associative property. Let us check for the identity element. So on the addition, 0 0 is the identity element. So I'm getting everything 0 0 0 1 1 0 1 1. On the multiplication, I'll have the identity element as what? So where we are getting all the elements, so I'm taking it as 0 1. So 0 1 is the identity element with respect to multiplication. I'm getting all the values 0 0 0 1 1 0. Sorry, 0 0 0 1 1 0 and 1 1. So the identity element is 0 1. Here the identity element is 0 0. Okay. Now what about the inverse elements? What about the inverse elements? So if you get wherever I'm getting, so the for 0 0 inverse element 0 0, for 0 1 it is 0 1. So addition, all elements are its additions. For multiplication, where I'm getting additive, so I'm getting 0 1 here, so 0 1 0 1. For 1 0, the inverse is 1 1. For 1 1, the inverse is 1 0. For 0 0, there will be no inverse. Why? Because 0 0 is the identity element with respect to the addition. So it is a field and it is a finite field. Now to represent these finite fields, we need to represent them by using the polynomials. Although we can directly define the rules for addition multiplication operations on n-bit words that satisfy the properties of GF of 2 power n, it is easier to work with the representation of n-bit words by using the polynomial of degree n minus 1. So how we are going to represent these fields, that is f of 2 power n fields, is by using the polynomials. So this is how we represent them. So a polynomial of degree n minus 1 is an expression of the form f of x is equal to a n minus 1 into x power n minus 1 plus a n minus 2 into x power n minus 2 plus so on plus a1 x1 plus a naught plus x naught. So to represent this n word, we need to follow some rules. So here the power of x defines the position of the bit within the field. So the LSB bit x power 0 defines the first bit, and x power n minus 1 MSB, the rightmost bit, is the position of n minus 1 bit. And we call these an minus 1, an minus 2, a1 and a naught as coefficients. We call it as coefficients. And these coefficients, what is the field that we are considering? 2 power n, right? So 2 means we'll have only either 0 or 1. So these coefficient values can be either 0 or 1. So we can do some operations on this one. So before seeing about the operations, let us see how we can represent an 8-bit word using a polynomial. So this is 8-bit word. Okay, so we can represent it as 1 into x power 7, 0 into x6, x power 5, x power 4, x power 3, x square, x power 1 and x power 0. Now if I take this, so I'll whatever the thing I am doing a multiplication with 0, I'll discard them. So I'll have x power 7, 1 into x power 7, 1 into x power 4, 1 into x cube, and 1 into x power 0. So as 1 is an identity element for multiplication, I can take it off, and after the final simplification, I can represent this as x power 7 plus x power 4 plus x power 3 plus 1. Okay, so we can do some operations on these values that we are going to represent using the polynomials. So an operation on polynomials actually involves two operations: operations on coefficients and operations on the polynomials. Like if these are the coefficients, we need to have operation on the coefficients. Similarly, we'll have operations on the polynomials. Okay, so in other words, we need to define two fields here. One for the coefficients and one for the polynomials. Coefficients are made of 0, 1, so we consider it as gf of 2 field, and for this purpose, and for the polynomials, we consider gf of 2 power n. So we need to know about modulus. You already studied about modulus operation. We all know about modulus. So before defining the operations on polynomials, we need to talk about the modulus polynomials. So addition of polynomials never creates a polynomial out of the set. Then there is no problem. That is, if you add two polynomials, the resulting of the addition of two polynomials will again belong to the same set. But when you are applying a multiplication operation between two polynomials, the output that we are getting will be out of the polynomial range. Then to bring it again back to the range, we'll divide or we'll apply modulus operation with respect to them. So for each degree, there is an often more one irreducible. There will be some polynomials which are irreducible. So whatever the output we are getting when we are applying multiplication operation between two polynomials, to reduce that one, we'll apply modulus operation with respect to the irreducible polynomials. So I have kept an examples for irreducible. These are all the examples for irreducible polynomials. So with respect to the polynomials, we can do two operations. Those are addition and subtraction. So addition and multiplication. If you do addition, it is like normal addition only. So if you consider these two polynomials, if you do the addition, so 0 plus 0, it is like an XOR operation only. 0 0 0 0 0 0 1 0 1 0 0 0 0 1 1 1 1 0 1 0 1 0 1 1. So the output that we are getting, so all the things that are having the coefficient as 0, we can omit them. So it will be 1 into x power 5, 1 into x cube, 1 into x power 1, 1 into x power 1 and 1 into 1. So it will be x power 5 plus x cube, x power 3 plus x plus 1. So here we'll have additive identity as well as we'll have additive inverse also. The additive identity in a polynomial is a 0 polynomial because adding a 0 percentage, here we'll have all the coefficients are 0. In the zero polynomial, what is the zero polynomial? In all the coefficients will have it as zero, then we call that polynomial as a zero polynomial, and the zero polynomial will be the additive identity for the operation addition. Additive inverse, the additive inverse of a polynomial with coefficients in g of 2 is the polynomial itself. So it will return the zero. It will return the zero. Why? Because here we are addition, we are calling it as XOR. What is the property of XOR? If you are applying the XOR between two same values, the output will be zero. The output will be zero. Okay, so we are considering zero polynomial as additive identity. So every polynomial will be additive inverse to itself. Okay, coming to the multiplication. So if we consider two polynomials here, so these polynomials x power 5 plus x power 2 plus x is applied, and multiplication with x power 7, x power 4, x power 3 plus x power 2 plus x. So what happens is, like, every x power thing in the first polynomial, that is x power 5, every element in the first polynomial should be multiplied with the everything in the second. So x power 5 into this entire polynomial, x power 2 into this entire polynomial, x into this entire polynomial, like this, x power 5, x power. Now we are getting these values. Now here the power having the same elements, the polynomial has same elements, will be cancelled themselves. So x power 9, x power 9, so they will be cancelled. So if you are applying addition between the same polynomials, we said that it will be given as 0. So we'll discard if you have 2. So we are discarded. So x power 6, x power 6, we can discard this one. X power 8, x power 8, we can discard this one. X power 5, x power 5, we can discard this. X power 4, x power 4, we can discard. X power 3, x power 3, we can discard. Then we are left with x power 12, x power 7, x power 2. Now, what is the main range we have considered? X power 5 and x power 7, but it has become to x power 12. It is out of the polynomial range. So we use an irreducible polynomial, that is x power 8, x power 4, x3 plus x plus 1 to get into the range. What is our range? Our range is x power 7 or x power 5, but it is x power 12. Okay. So if you do the division, that is modulus operation, if you do x power 12 x power 7 plus x squared with respect to this irreducible polynomial, that is x power 8 plus x power 4 plus x cube plus x plus 1, then we are getting the output as x power 5 plus x cube plus x squared plus x plus 1. This is within the range of the given polynomial. This is how the multiplication operation is done with respect to the polynomials. So this is how the division is done. This is how the division is done. So with this, we have covered the mathematics for symmetric cryptography. So what we have covered, the mathematics symmetric cryptography is what? Algebraic structure. So what is the algebraic structures we have considered here? The algebraic structures that we have considered here are group, field, group, ring, field, and again we consider finite field. Again, from this finite field, we have considered about Galileo's field, where we consider the element within the Galileo's field is all prime numbers, and then we are considered, as we are we communicate in the computer, we cannot consider the f of p. That's why we have gone for gf of 2 power n. So we can represent this gf of 2 power n using the polynomials. So we have seen the properties of polynomials. So when you represent the polynomials, it will be in the form of coefficient and a polynomial. Then we can apply two operations on the polynomials, addition and multiplication. That's what we have covered in this lecture. So in the next lecture, we are going to see about the modern symmetric ciphers. Thank you.